During atmospheric re-entry, the belly of a spacecraft is engulfed in superheated plasma, pushing surface temperatures past 1400 degrees Celsius. Historical capsules burned off a blade of material to survive this heat, but a vehicle designed for rapid turnaround requires a mechanical, reusable ceramic thermal protection system. The sheer physical scale of this requirement becomes obvious when looking at the windward side of a super-heavy vehicle. To cover this massive surface area, the current design uses approximately 18,000 individual hexagonal tiles. Instead of being glued down, these tiles are mechanically pinned directly to the steel chassis to allow for immediate replacement. When you total up the volume of those 18,000 components, you are looking at roughly 5 metric tons of specialized ceramic material per vehicle. This creates an absolute physical limit. The cadence of an orbital fleet is strictly capped by our centralized industrial capacity to manufacture, inspect, and replace these 5 tons of silica heat shields. The material science behind these tiles is highly specific. The silica used cannot be standard crystalline quartz. It must possess an amorphous, disorganized molecular structure. If you expose a rigid crystalline lattice to the sudden thermal shock of re-entry, the material will instantly shatter. For decades, the aerospace industry has sourced this material by mining high-purity crystalline quartz sand out of the earth. Because that raw sand is crystalline, manufacturers have to apply brutal thermodynamic force to break the molecules apart and create the required amorphous state. Breaking those bonds requires melting the quartz in an electric arc furnace, driving temperatures up to 2,000 degrees Celsius. There is an alternative supply chain that skips this thermal penalty entirely. BiogenicSilica, extracted directly from agricultural bamboo, is naturally amorphous from the moment it is harvested. Fueling a high-cadence, reusable space fleet with energy-heavy mineral processing creates a thermodynamic bottleneck that plant biology has already solved. Certain grasses, particularly bamboo, act as active silica sponges. As they grow, they draw monosilicic acid out of the soil water to build a natural defense mechanism against herbivores. This diagram compares the two processes. On the left, the arc furnace blasts a crystalline lattice. On the right, bamboo natively deposits drawn silica into its cell walls. It performs the same structural restructuring as the industrial plant, but passively over its normal growth cycle. Because the plant delivers the silica pre-amorphized, refining it for aerospace use requires low-temperature aqueous chemistry, staying completely below the boiling point of water. Eliminating the furnace stage drops the total thermal energy demand by an estimated 60 to 80% compared to the mineral baseline. Shifting the raw material from mined quartz to bamboo moves the massive energy burden of aerospace manufacturing off the local power grid and directly onto passive photosynthesis. To extract this biogenic silica, the bamboo leaves are harvested and calcined at 600 to 800 degrees Celsius to burn away the organic material. What remains is a concentrated leaf ash containing an exceptionally high 75 to 82. Laboratory analyses confirm this precise sequence consistently yields a final product with 98 to 99.7% purity, satisfying current aerospace tolerances. Beyond pure chemistry, the plant-derived material has a unique physical structure. The biogenic silica nanoparticles are natively mesoporous. These microscopic void spaces act as built-in insulation. The trapped air drives the thermal conductivity down to less than 0.1 watts per meter Kelvin, essential for resisting re-entry plasma. This natural nanostructured architecture results in a material that is structurally optimized for thermal insulation per unit of mass, surpassing the performance of denser mineral fibers. To see if this process can actually support a space program, we have to look at the biological yield ratios. Dry bamboo leaves yield about 15 to 19% recoverable high-purity silica. To produce the 5 metric tons needed for a single vehicle, the extraction process requires up to 33 metric tons of dry bamboo leaves. Scaling that up for 100 flights per year multiplies the biomass requirement to upwards of 33,000 tons of dry leaves annually. At that maximum flight cadence, the total industrial output required is roughly 500 to 1,000 metric tons of pure aerospace silica every year. In a managed plantation setting, a conservative agricultural yield is 20 tons of biomass per hectare annually. When running the math against those yields, fueling a fleet of 100 super heavy ships requires a maximum of just 3,300 hectares of dedicated bamboo cultivation. You can build a carbon-negative thermal supply chain for the most ambitious spaceflight program, using a geographic footprint smaller than a mid-size regional airport. Finding that specific acreage requires looking at regions with established biological capacity. Kenya stands out as an immediate strategic candidate. The country currently possesses an estimated 133,000 hectares of mature, naturally occurring, and introduced bamboo resources. That existing inventory vastly exceeds the maximum 3,300 hectares an operational aerospace fleet would demand. The region also has the regulatory framework already in place, formalized in the 2019 Kenya National Bamboo Policy. This mandate actively supports commercial cultivation, targets large-scale land restoration, and incentivizes high-value export integration. Logistically, a new supply chain would center on dedicated agricultural cooperatives, geographically contained within 300 kilometers of major industrial processing hubs like Nairobi. For the domestic economy, this creates a high-yield industrial sector capable of generating thousands of rural agricultural jobs, while simultaneously capturing premium foreign exchange capital. Kenya holds the biological inventory, the land capacity, and the specific state policies required to secure a first-mover advantage in this specialized biogenic silica market. While the extraction chemistry is mature in a laboratory, integrating any new material into an active aerospace program is extremely difficult. Aerospace certification is an unyielding process. It requires flawless, multi-year batch qualification, testing, and total molecular traceability for every component that touches a vehicle. Shipping processed quartz sand from a mine relies on uniform, predictable logistics. Managing millions of tons of leafy biomass introduces complex seasonal variability and inconsistent moisture contents that must be tightly controlled. To de-risk this transition, the strategy starts with Phase 1. This involves commissioning a specialized pilot extraction plant in Kenya, producing 100 to 500 tons annually. Once proven, Phase 2 provides this material to contractors for prototype tile manufacturing and rigorous arc-jet thermal cycling tests. Early engineering adoption might avoid full replacement entirely, instead utilizing hybrid tiles that place a highly insulative biogenic core underneath a traditional mineral outer coating. The final objective is Phase 3, establishing long-term commercial supply agreements that directly link rural agricultural outputs in East Africa to orbital infrastructure. The next generation of heavy spaceflight demands extreme material efficiency. We can achieve it by shielding advanced exploration vehicles with a sustainable agricultural byproduct.